Hello everyone, my name is Azari. I'm an assistant professor at the University of Alberta, as well as a Canada CIFAR AI chair at Amii, the Alberta Machine Intelligence Institute. And today, I want to talk to you about the work that I'm doing in machine learning for the exploration and scientific understanding of planets, specifically the ones in our solar system. So I just want to start off with just kind of this big picture of kind of how I see machine learning in our field. And how I see it is that planetary science and planetary exploration requires machine learning at this point in time. We have a lot of data. We are often dealing with automated needs for exploring planets, but out-of-the-box methods in particular are insufficient for answering our scientific questions. So kind of applying some of these basic kind of tutorials that you would find about machine learning do not always result in us increasing our understanding about a planetary environment. And so what I want to do today is present to you a vision of how we can kind of alter out-of-the-box methods, how we can include physics, so that we can actually answer the scientific questions that our field of planetary science and exploration are particularly interested in. So to motivate us, I just want to provide an example. And this is an example that I find particularly compelling and illustrates kind of this interplay of machine learning and physical sciences. So in late 2022, the solar wind effectively disappeared through an entire swath of the solar system. Now, what is the solar wind? The solar wind, you can think of it as a flow of charged particles or plasmas that occurs throughout the solar system. It is sourced from our sun, and every planet in our solar system interacts with the solar wind. You can kind of think of it as an ocean that occurs in our solar system. We don't always see it, but every planet is interacting with it, all right? Now, just as a bit of a disclaimer, obviously, these diagrams are not going to be to scale. The sun is quite a bit bigger. We're missing Venus and Mercury here, partially because I study Mars a lot, and we all live on Earth, all right? So in 2022, late 2022, December, the solar wind effectively disappeared, all right? Now, what this actually looks like in our data sets, this is the data from upstream of Earth. Usually you would expect the protons, or these charged particles that make up the solar wind, to exist between about 4 and 8 particles per cubic centimeter, right? So it's not that dense, but it does exist. But if you look specifically at December 25th to 26th, the proton density that we have measured from a satellite upstream of Earth has effectively gone to 0, right? So this means that the protons have effectively disappeared. Like, there is no solar wind carrying particles at this point in time, right? And this changes a lot of what the Earth interacts with in terms of solar wind dynamics. It changes a lot of how we would expect to predict space weather, etc. Right? But what I want to focus on is Mars, because the same exact event occurred at Mars, right? The sun is a large object. If the solar wind has a massive density decrease at Earth, you would also get the same thing at Mars, dependent on if they are close in alignment. And in this particular case, in late 2022, they were, right? Now, how we study this is with a mission called Maven. Maven is the, let's see if I can remember the acronym, the Mars Atmosphere and Volatile Evolution Mission. The main goal of Maven is to understand how Mars's atmosphere was potentially lost in the past from studying our observations of Mars today, right? So Maven orbits around Mars. This is an example orbit from 2019. And as Maven orbits, it passes through the solar wind, which I'm demonstrating here with these arrows. We have a velocity flow of these charged particles that I was talking about before. And as Maven orbits around, it rotates between measuring the solar wind and then measuring what is happening downstream from the planet, right? And so this bow shock characteristic that I've shown here, that is because, kind of similar to how the solar wind can be thought of as a fluid flow, Mars can be thought of as a boat existing on this fluid flow, or this ocean of solar wind. If you've ever gone in a boat on the ocean before, there's a shock front that forms in front of your boat. that is effectively the same thing that is happening with this bow shock. Now, Maven has existed around Mars since 2014. Right? This is now approaching over a decade of measurements. We have over 20,000 orbits that all kind of process around the planet, so they're measuring different locations around the planet. And they're all measuring kind of this combination of solar wind, downstream effects, 20,000 times, right? So if you have an event like the disappearing solar wind event that I talked about before, why can't you just use the suite of instruments that we have on board Maven to study that, all right? So Maven is, I like to think of it as a large data collector. There are multiple different instruments that are all collecting different types of observations. We can get magnetic field observations, we can get plasma wave observations, we can study the neutral atmosphere, we can study the charged atmosphere or the ionosphere. And with all of that, we have a ton of data in which we can kind of create large statistical pictures. And that is often what our field does in this case, where what I'm showing here is from a previous work where we took all of the Maven data that we had, and we created kind of this three-dimensional picture of what we think is happening in that space. And so these colorful lines basically connecting a vector field just by tracing. And this type of study is very useful to do. So why don't we just do statistics and machine learning to study this type of event? We have 20,000 orbits. Why can't we just apply some, clustering algorithms, et cetera? And the reason why is because we don't actually have all the information that we need, all right? So the thing about space environments, the thing about planetary science, is that these are big systems. And one of the problems with applying machine learning is that we can't always quantify everything that matters. And one of the things that matters is the sun in this case. And our sun is dynamic. And in particular, it has a dynamicism that has a peak every 11 years. So on the left, what we're looking at is the sun in 2019. This is from the Solar Dynamics Observatory, so this is real data from our sun. And the video is not going to show again. In 2019, we had a very quiescent sun. It was during solar minimum. In 2024, we had a very active sun. This was during solar maximum. And we are relatively confident that solar maximum corresponds to when the sun's internal magnetic field is reversing, all right? So normally the sun has a dipolar magnetic field, but every 11 years it reverses. And during that reversal, the magnetic field becomes extremely chaotic, right? Now we can't see magnetic fields, but if you could, it would roughly look something like this. Where on the left, we have a pretty dipolar configuration. Magnetic field is leaving from the north, coming in from the south. And every 11 years, this dipolar field reverses, right? And during that reversal, it becomes incredibly chaotic, right? And so we have this extremely chaotic magnetic field orientation, for example, on the right here. And this chaotic orientation creates these little clusters of very intense magnetic fields. This keeps the plasma environment of the sun quite cool. If you look at the sun during an active period, you will see sunspots, all right? Now, you can see these with your naked eye. I do not recommend it. I highly do not recommend looking at the sun with your naked eye. But oftentimes how we track if we're in solar minimum or solar maximum is that we count sunspots, right? And we have been doing this for a very long time. Okay. So you might notice it's 2024. As a bit of a preview, we are in solar maximum right now, all right? Now, what happens during solar maximum, you have more sunspots, you have more chaotic magnetic field, and that drives events throughout the solar system, all right? So during May 2024, so very recently, we had one of the largest geomagnetic storms on Earth in the last 30 years, right? This geomagnetic storm drove a ton of auroras that most people in Canada should have been able to see with their naked eye. If you are particularly interested in the aurora, you might have gone out and seen them like I did, which is where these pictures are from. So these are pictures of the aurora in Manning Park. in British Columbia, and those were taken with just a normal cell phone. Right? Now, the kind of operational study of how the sun impacts planets is known as space weather, and the most positive aspect of space weather for humanity is these beautiful light shows in the aurora. However, space weather does have particularly negative effects on Earth's power grid. It can disrupt satellite operations. It can deorbit satellites in particularly problematic ways, waste a lot of money, because if you launch a satellite, you want it to stay up, all right? But at Mars, we're particularly interested in how these kind of rare solar weather events, or space weather events, are going to affect our planets, right? So as I mentioned before, you can track the solar cycle with sunspot numbers, right? I'm showing you the record up until kind of the early 1980s, the mid-1970s. However, this record goes back pretty well estimated until the mid-1700s, right? So sunspot tracking is something that you can do with very limited observational equipment. So you can take this record back quite a bit. And you can see that we are in solar max right now. Kind of the pink curve on your right is what we think is going to happen. So these are predictive models. But where we are right now is kind of this 2025 early to mid zone, right? And you can see, some solar cycles are larger than others. Sometimes the activity is higher. But in 2014, this mission to Mars arrived, right, which is this kind of dashed line here. And then the event, the disappearing solar wind event that I was talking about, where the solar wind disappeared, is kind of late 2022, right? And the thing about that is if you're trying to build some model based off of prior observations, you have never actually seen the same time in solar cycle before this event occurred, right? So this is the rising phase of the solar cycle. We were not there when Maven arrived, right? So this is the first time that you're in this particular parameter regime. It's the first time that Mars has been driven in the same way. And so successfully building a flexible data-focused model, you need sufficient observations over the entirety of your parameter space that you're interested in. And quite frankly, we just don't have it, right? 10 years is a lot of data, but it's just not enough in the parameter space that we actually care about, that we know matters, right? And so this is kind of this ubiquitous problem in planetary science, where we have a lot of data, we have to use it in an automated way, but this data set is inherently sparse. Maybe we weren't in the right place over the planet at the right time. Maybe the sun was in a different part of its phase, and therefore building some sort of kind of data-focused model is just not going to allow you to have the insights that you want to have about this particular event. So what do we do instead? As a field, ooh, we get some music. So we're not going to play that because it's actually a little loud, but we're going to skip ahead a little bit. So as a field, we tend to build these large physics-based models. On the previous slide, if the video was not as loud as I would have preferred, you would have seen this time-dependent simulation in three-dimensional space, where we're solving some sort of physics-based equation. In our field, we tend to focus on fluid dynamics and electricity and magnetism equations. And that combination describes the space environments of planets that we actually want to study, okay? And this tends to be how we address questions like what happened here, how related is that to what happened over there, right? And that's exactly what we did for this particular event. So these are model representations with some artistic interpretation as well of what happened around Mars during this solar wind event, both before, so a nominal condition, and then after, or this very abnormal condition. And along these orbits, we have these kind of fringe, kind of fur-like vectors. That is our ion density, okay? And so what we can see is that the ion density changed significantly between these two events. We found that out with this physics-based model from one of my collaborators at UCLA, Yingxuan Ma. And with this type of kind of scientific modeling effort, we were able to make some conclusions about the system. All right. But at this point, you're probably asking, this is a machine learning talk, where is the machine learning here? And I want to take this a little bit further and say, what if we want to extend our understanding a little bit deeper? So what if we want to ask, what model parameters actually best describe our data? Or better put, what set of model parameters best describe our observations? If we are able to answer that, then we can better use our physics-based models to the extent that we have the capacity to, right? Now, there's a bit of a problem with this, and that is that the physics-based models that we run, so those models that I was showing you before, they are computationally intensive, right? So one parameter input of that physics-based model might take a day, 2 days, 3 days, possibly up to a month on the best supercomputers that we have access to. And additionally, our observations are quite limited or sparse. So as you remember I was saying, this is the first time we've seen this type of event because it's the first time we're in this particular phase of the solar cycle. And so you're also limited on the data side, okay? So if we want to, in this case for Mars science, estimate which distributions of model parameters, i.e. the physical conditions that we're interested in, describe our limited observations, right? Then we have inherently a problem. It's simply just too computationally intensive to actively solve this. If you are kind of frequenting the geophysics space, this is often known as an inverse problem, okay, where you are actually trying to figure out not the forward, but the inverse of this particular estimate. So how we are currently solving this in the field, and how I would like for us to kind of continue solving this in the field, is that you can run your physics-based model over a varying set of parameters. You can then create an emulation of your physics-based model, so you can train an emulation with machine learning. And there's a lot of different models that you could put in here. And then finally, once you have an emulator that runs faster, you can solve this effectively through sampling, or you can treat it like a Bayesian inverse problem. And this gives you the ability to really put your physical model to work, right? So I want to be clear here, this cannot effectively replace physics-based modeling. You still need them to create emulations. But what it does do is it enables us to solve questions in the field that we have not been able to before. Oftentimes we'll run maybe 5 to 10 model runs, and that's all you have time for. With this type of chain, you can actually inquire to a lot of the different physics that is happening in the system, right? So my research focus in this particular area has been in including additional uncertainties, right? So as a physics-minded person, kind of creating emulations of your very high accuracy, high fidelity physics-based model makes me a little bit concerned. And so my focus has been, what if you have an emulator that is aware of when it is wrong, right? Or aware of its own uncertainty about this emulation chain, and then you include that uncertainty in your final estimation, then effectively you're able to go ahead with your physical conclusions, right? And so I want to give you a preview of what this looks like, right? And before I give you a preview, I just kind of want to take a step back and say, this is a common problem in the physical sciences, right? We often have physics-based models which are expensive. This creates a bottleneck in a lot of the types of questions that we're interested in answering. So for example, if you want to estimate the solar wind conditions at Mars, if you want to estimate what is inside different planets, what does the core of Mars look like? What does the ocean underneath Europa look like? The way that we do that is with physics-based models and running different inverse problems. This enables us to actually get deeper into the science that we're interested in doing, right? Now, unfortunately, the PowerPoint conversion between my computer and the presentation computer did not work. So you'll see that the data and my uncertainties are missing. So I have to take my word for it. And you'll have to imagine that this particular match between our data and our predictive models actually really good. And so after, you can ask to look at it on my computer. But this is the case that we were running this simulation-based inference problem on, where what I'm showing you with this like cone-like figure is an orbit of Maven. And as Maven progressed around its orbit, it saw a specific event that occurred between 11 a.m. and 12 p.m., where our observations changed. And our question was, why did they change? All right. So one of the first things we did was we estimated, okay, well, how well does our physics-based model plus machine learning model? So these solid lines are actually our emulated or forward model from the machine learning emulation. How well do they match the data? If you could see, they did match the data quite well. But really, the point of this entire chain was to be able to estimate what type of physical parameters actually described that match, right? So again, this is another PowerPoint conversion issue, but what we're seeing here with these solid lines is right at that time of transition, our emulated model of our physics-based model would estimate that the conditions that we're interested in, and I'm showing you multiple physical parameters that we were interested in, did in fact change at that time, all right? And what's particularly nice about this application, which unfortunately you can't see, is every single one of these lines have an uncertainty envelope on them. And that uncertainty envelope gives us understanding about how confident we are, because we don't actually have a lot of data. And so there is going to be some inherent uncertainty in problems like this, right? So this type of method is not just useful for Mars. You can additionally run different types of planetary environments through this. So this is another example where instead of saying we have some data that we're interested in matching, what if we say instead, what is our possibility of success if we send a mission to a specific planetary space environment? In this case, I'm showing you Europa. We have several physical models of Europa. And what is the chance of a spacecraft trajectory, so this dashed line, actually being able to recover what Europa's atmospheric surface density and scale height are? Now, the reason why we're interested in those two quantities is that tells us how potentially life-supporting a planet like Europa could be, right? Would we expect to see different types of life forms, microbes, etc., on a system like Europa? Well, we would answer that particular question if we are able to estimate the atmospheric compositions, its density, and with that, we can answer questions like, what is potentially underneath the surface, right? So this particular method is extremely useful for estimating what is the possibility of success for future planetary missions, right? Now, with that kind of deep dive into this very kind of subset of the field, I want to give you this a broader picture of an overview of how people are using machine learning in planetary science. So I've shown you one particular case. I now want to show you some other cases that people are pursuing and where I see kind of the field going in the future, right? So the reason why I started using machine learning, and I think a lot of people in my field are interested in using machine learning as well, is because, quite frankly, we are drowning in massive data sets, right? So I would peg the beginning of our field to starting in about the 1970s. This is when specifically in situ observations were obtained from other planets. The Voyager spacecraft are very famous, and those are kind of what I would consider a hallmark of in situ planetary exploration. The data size of the Voyager spacecraft is about 100 gigabytes. It's not that large, right? So you can truly go through the entirety of the Voyager data set with your eyes and just kind of look at everything. And that is often what we do as scientists. But if you leapfrog to the modern era, we have missions like the Mars Reconnaissance Orbiter, as well as Maven, which are now collecting more data than missions of the past all combined, all right? So these are massive data sets, and these are really pushing us to consider how we can use automated methods, machine learning or otherwise, to kind of inform our scientific understanding, right? Now, planetary science is not particularly the most data rich, as we've kind of discussed before. We're missing certain parameter regimes. If you expand your view to kind of all of space and Earth science, you have missions like MMS, which is a mission at Earth. This is collecting about 13 gigabytes of data per day. So every day, we are collecting more and more data. This is actually a mission of 4 distinct spacecraft. Then we have missions like the Solar Dynamics Observatory. That's where those solar pictures, those solar videos are coming from. This is collecting about 1,500 gigabytes of data per day. And then if you leapfrog into Earth observations and climate science, we now have missions like the Sentinel series, which are collecting 20,000 gigabytes or 20 terabytes of data per day, right? So these are really pushing us as a field to consider how we can start to include machine learning in just our normal scientific process, right? And at a very kind of high level, how we tend to work is we will formulate some type of hypothesis, a question. We will then investigate that answer with several different methods. We have kind of the classic experimental and observational methods, telescopes, spacecraft, those kind of fall into there. We have theory, i.e. mathematics and how we can kind of describe physical systems. We have computation, those physics-based models I've been talking a lot about. And then finally, we have data science, right? And data science in particular is a kind of emerging area that we are considering how best to use these methods to describe our systems, right? So with this in mind, then how are we actually using kind of data science and planetary science? And the answer is in a lot of different ways, right? So we can do pre-mission planning. So this is like if you sent a spacecraft to a specific object, say Europa, what is your probability of recovering what you thought you should recover, right? Where should you send a spacecraft? If you have, say, a rover on Earth, how analogous would that be to what you would see on Mars, right? And so pre-mission planning is where a lot of activity is happening for machine learning. There is also a significant amount of attention in mission operations. So this is stuff like, because you're really far away, you're not going to be able to operate with a human in the loop. You'll have to have some type of time lag, right? So this is autonomous operations. It's also, you can prioritize different observations as well. Let's say you saw something interesting. Because humans are far away, you need a way of dynamically and automatically saying what is interesting without asking a human, right? And then finally, we have kind of bread and butter science, which is post-mission analyses, right? And post-mission analyses are kind of what you would consider to be most of the focus in the field right now, which is including data into physical models, including machine learning into physical models, resolving kind of what we understand about the system, describing these large physical systems, as well as kind of using the amount of data sets that we have to better describe kind of our scientific understanding, all right? And from about 1995 onwards, kind of similar to other fields, planetary science has seen an increase in the use of machine learning. And so what these lines are showing you is the 4 NASA-represented science domains: planetary science, earth science, heliophysics, so this includes space weather and space physics, and then astrophysics. And over the last several decades, we've seen that the use of machine learning has increased. But I want to point out that planetary science has not seen the same type of increase, right? And in particular, if you kind of run the numbers, we would estimate that it's about half as much as other fields that have analogous types of data sets, right? So earth science data sets are very similar to planetary science data sets. And so the question is kind of, why is this happening? And I would pose that the answer is that our data sets are large but sparse. We don't always have those types of measurements that we'd want. The sun has an 11-year cycle. You have only been in orbit for 10 years, right? So like these types of questions about sparsity, about how you would include physics-based information, have become very important in planetary science. And they have really driven kind of the machine learning users in our field to start to consider how we can incorporate physics-based models, right? And so how I like to think about this type of regime is that we want to be able to include our physics-based understanding as much as possible, right? But we want to also include as much of the data sets that we have available to inform our understanding. And you can think of this as this spectrum, where on one side you'll have a completely model-bound or theory-based type of approach. So this would be running physics-based models. So on your left, an example of this would be the type of physics-based model that I was showing you earlier for understanding a plasma environment, right? And then on the right would have, you don't necessarily care what type of model representation you have, but you do care about its predictive capability, right? Then you want something that is very informed about the data that you have, but you can have a bit more flexibility in the type of model. And a classic type of application of this is, say, you want to forecast solar flares for humans on Earth. A good way of doing that is truly deep learning at this point in time, all right? So this in-between area, I think, is particularly rewarding for us, where your goal is really to increase the transparency in your findings. You want to include what physics-based knowledge you already have, right? We've built this up for the last several centuries, and it's worthwhile to include that. And this has been kind of renamed, reinterpreted a lot. I like to consider it model-adjusted machine learning, right? So you're literally adjusting models. But this has also been discussed as theory-guided, interpretable, which is much more of a common term these days, physics-informed, which is also very common, or domain-aware, all right? And this is really where I see the field going for planetary science in particular, right? And so with that, I'll leave you kind of with this perspective, which is we have a lot of data, we have to be using machine learning, but current out-of-the-box methods are insufficient without significant alteration for answering most of our scientific questions, which I think we can do, all right? So with that, I will take questions in the remaining approximately 11 minutes. I don't actually know how we take questions.
I think it's over here.
Ah, thank you.
Hi. As a fellow physics nerd, hi.
Hi, welcome.
So, hey, I assume some of your physics-informed models, we're talking the combination of Navier-Stokes, Maxwell, and GR, and maybe a few others peppered into the mix too. Computationally intense, tensor, vector. Those models, very well understood, computationally intense, as you've said. One area I've kind of played with in the industry I work in, just dabbled really, not into the same data depth as you do, is, as you said, kind of sampling that parameter space out and then trying to inform whether it's a neural network or a classical statistical machine learning to emulate in a more faster regime. Now, are you using the complete model and trying to sample out that space? Or are you using subset models to sample out their parameter spaces and then combining them together to orchestrate, and understanding there are error bands, like every time you twiddle the knobs in the parameter space?
Yeah.
Yeah, just, yeah, holistic or a subset?
Yeah, so what I showed you here is very much a subset. Some of the work that we're doing now is the full three-dimensional model. So the thing about these models is we are interested in the spatial correlations between different grid cells, and so you do want to have the entirety of the physics-based space to emulate it successfully, right? So like, if hypothetically you actually want a different spacecraft trajectory, then if you've only emulated a part of the model, you're not going to really be able to use it as well as if you had done the whole thing originally. So some of the work that I've been doing very recently is using scalable Gaussian processes with some collaborators of mine at University of British Columbia to rapidly estimate with uncertainties these full three-dimensional spaces. And it is wildly computationally expensive, but estimating those uncertainties is something that I think we need to do if we're going to be emulating.
little follow-up in the tiny industry I work in oil and gas. When we have to run, say, the Navier-Stokes or fracture mechanics or other things, we've got decades where we've run these models. Have we been good at collecting and curating that corpus of information? Sometimes yes, more often we're getting better at it, to then kind of train on the subsets and then kind of have that pairwise emulator like that backwards calculation where you're pre-emulating, here's what I'm seeing, what fits the model. Is it a well-sampled space? If I do nearest neighbors, KNNs, or whatever else, am I in a well-sampled data set or am I not? If I'm not, can I now run my more expensive physics models to populate that space out and make it better overall going forward? I don't know if there is a question in there, I'm just talking.
Yeah, so I think to kind of summarize it a little bit with a kind of overview for people, kind of preset runs will only take you so far. You want to be able to dynamically pick where you would actually run a true physics-based model so that you can have this trade-off between high fidelity and low fidelity models, and that would be kind of the ultimate virtuous scheme for something like this.
The dynamic feedback, yeah.
A dynamic system where you're saying like, oh, well, the uncertainty is very high here. We actively want to run a new model run here, and that is something that we've been looking in. So, yes.
Thank you
it's a
for
good
answering
idea.
the question I didn't know I had.
Yeah.
Thanks.
Hi, awesome talk. I was kind of wondering what your general strategy is for dealing with, for example, emulators are notoriously bad at not actually obeying physical constraints like mass conservation or your divergence-free condition, stuff like that. So how do you know what data to actually trust from your emulator versus what you should just throw out because the magnetic field was not divergence-free 5 minutes ago? So.
Yeah, so I'll answer it in a non-machine learning way and then a machine learning way. The non-machine learning way is that we are working significantly with modelers in order to only run these types of systems where we truly believe that first, the model is actively a good description of our observations. Right, so models themselves don't always fully describe your observations, and so you do need to be a little bit careful of that. It's also possible that you can push a model into a parameter regime where it's not numerically stable, and so you need to be very careful about that as well. So the kind of non-machine learning answer is that we're working with domain experts to make sure that we only run these types of systems where we can trust the results. The other answer is we're including uncertainties. And then the final answer is that we've started looking into constraints, regularizing our emulators to make sure that they would follow some of the very basic conservation quantities that we're interested in, right? So merging that subset of emulators with the physical models, which are highly constrained. Right?
Okay, cool, thank you.
Thank you.
Hi, a really nice talk. So I think I'll be just having a follow-up question from the previous question. So like if you have a time series or time-dependent simulations, if you have a, say, surrogate model or say that the emulator that you are using, when do you expect these emulators to be, say, have kicking in the time series simulations, or you would like to do, say, longer time series with true simulations, or you can decide which ratio of these emulators versus the true simulations to have?
Yeah, so time-dependent simulations are kind of the next, I would say, focus of this work. We have currently been focused on simulations that you'll run until a steady state scenario. So you'll have a parameter, and then you will run that model forward in time until the solution has effectively converged to your final solution. That is a much easier problem. So we're handling it on the physics side, on the model side. We are interested in doing time-dependent simulations. That is a little bit more tricky. I am interested in ideas that people have.
Yeah, because we are having a similar situation. So we are material scientists, and we have a similar problem in that case. Probably.
Yeah, it's a particularly tricky issue because the solution does, change based off of time. Right now, we have moderately made a physics-based assumption to get around that, right? And so as a field, we often will run a model into a steady state condition, and that is then what we choose to emulate. But that doesn't really cut it for systems that are very dynamic and time dependent, right? And so, yeah, I'd be interested in hearing what you have to say after.
Yeah. Thank you.
Hi, thanks for the talk. Just a quick question that's related to OML. You mentioned 11-year cycles of reversal of polarity. Does that also correspond to higher temperature on Earth when there's a chaotic solar activity?
Yeah, so there's a lot of, I would say, deep modeling, and not by deep learning, but just intellectually deep modeling in solar impacts to, I would say, kind of climate dynamics. To our best understanding, there are some obvious impacts. The sun is a massive source of heat. And you will go back into the records of solar cycles and you'll see distinct periods, that some of which are kind of known, such as the Maunder minimum, where sunspots were very, very weak. We don't necessarily know what was happening with the sun at that time. Extending the climate record back to that period is very tricky. And so there is research into that. I would say as a percentage of impact, the kind of specific amount of sunspots versus Earth temperatures is not a huge amount of driving. There are other physical quantities that we would be more interested in than sunspot number. And I would say that's an ongoing point of research, but to our kind of best understanding, most of the kind of recent increase of temperatures is truly human driven. So, other questions? Otherwise, we can take a 2-minute break. And I think I'm actually maybe possibly over. The timer says orange. So with that, come find me after if you have any questions. Thank you.